So this is another frame which we are going to solve now using the Kinase method. Now again with all the basic criteria of sway, we will try to understand whether this frame is supposed to sway or not. First condition is to observe whether there is a horizontal force. So there is no horizontal force, so there will be no sway because of the horizontal force. Now let us look into unequal distribution of load, column length and sections. Okay, so if you observe the distribution of load, it is evenly distributed, it is symmetrically distributed, and looking at the sections of all the column, it is remaining high, so it is not going to sway because of the change in the sections also. Now looking at the length of all the columns, the column length are also remaining same. So this is the two-storied frame that we have. So here what we need to do is we have realized that this frame is not supposed to sway, so this frame will solve with a non-sway condition. So again, taking the benefit of a symmetrical condition, what we can do is that we can separate out one side of the symmetry. Okay, so but before we separate out one side of the symmetry, what I would like to say is, let us observe this entire structure and look at these two columns. These two columns are acting at the center. Okay, so whatever the load that is divided on either side of this column will be of symmetric in nature. Because of that, there will be no movement generated in this column. Okay, whatever the force that is acting, it will be an axial force and it will be going towards the foundation. Okay, so these columns are not subjected to any kind of movement because you can see that the load on either side is symmetric. Okay, now if I have to explain you in the more simplest manner, you should understand the arrangement of seesaw. Okay, so you know that there is a platform on either side, then we have pivot on this side. Okay, so this membrane or this post that is below this pivotal point, if the load is same on either side, the forces will be exerted is in the downward direction only. Okay, now imagine if the weight on any of the side increases. If the weight increases this side, so what will happen, this plank will go in the downward direction and this will go in the upward direction, creating a moment here, right? So movement generates only when there is an unequal distribution on either side. If the distribution is equal on both sides, then the load that is going will be of concentrated force itself. Okay, so whenever we have balanced load on either side, there is no movement that gets generated here. Okay, now imagine this pivot functions only when there is a moment that is applied. When the moment gets applied, when there is a difference in the loading. If the load is same on either side, okay, the length of these members are also remaining same. In that case, the moment will be equal to 0 at this pivot. Because of that, this will be in equilibrium condition and the force is going in the downward direction only. Okay, you need to imagine in a way while analyzing a figure, while analyzing a frame, how this moments and forces will function. Okay, so if you see in this frame, the load on this side and load on this side are equal. Because of that, the moments in these columns will be equal to 0. So MHF and MFH will be equal to 0. MFD and MDF will be equal to 0. So the moments will not get generated, but the forces will get generated. The reactions that get generated will be transferred to the foundation. Okay, so that is what you need to understand. Okay, now what I'll do is either I can take this part of the section or I can take this part of the symmetry. So let us take this part of the symmetry. In this symmetry, if you see in the previous problem, what I did is I took across the center of the symmetry, right? So here also I am taking across the center of the symmetry. So this is the center of the symmetry. If I remove this, if I take out this part of the symmetry, I'll have columns and beams. Okay, now if you see the previous problem, if you observe the previous problem, I had written these values as D dash and E dash, if you remember them. Now here I am writing it as D and E itself. Okay, earlier when I took the symmetrical part, I had cut exactly at the center of the frame, right? So it has cut the beams in the previous problem. Now I am not cutting any beam. I am removing the beams from the joint D and F. Sorry, this should be F. Okay, so I am removing this symmetry at these two joints D and F. So this total length has to be considered now. Earlier I have considered half of the length. Okay, now I have to consider the total length of the beam CD and BF. Okay, now I have taken this part. Now AB, BC, CD and BF. So these are the this is the part of the symmetry which I have chosen. Now the next thing what you need to do is to calculate the fixed end moments. So you can calculate the fixed end moment at MFBF and MFFB, and then we can calculate how much is MFCD and MFDC. Okay, so these are the values that I have calculated over here. Now once you calculate the fixed end moments, next step is to solve for the rotation factor. So the rotation factor can be calculated by calculating the stiffness values at any given joint. So joint B consists of BA, BC and BF, so as I have written here. Okay, right. So let us look at the value of stiffness of BA. What is BA? The value of I is I, and length of BA is 3 meter, so I by 3. Now similarly BC is I by 3. Now going to BF, so the value of I is 2 times of I. 2 times of I divided by the length of member BF is 6 meter, so 2I divided by 6. Now you might ask me the question, in previous problem what we did was we divided half of that, so half of I by L we have taken, but in this case I am taking complete length, complete value, which is 2I by 6. Now see here, earlier when I cut it, I cut exactly at the center of the beams, right? So only half of the length of the beam was there. Now when I cut this section, when I removed the symmetrical part of the frame, now I am taking the total length of the beams, right? So in the previous problem I had taken only half of the length of the beam. Now I am taking the full length of the beam, so that's why I have to consider the full length of the beam. So in this case I am not going to use half. So earlier what I did, I used this while calculating the K value, I had used half of I by L. In this case I am not going to use this, I am going to use only I by L. So what is I value? I value is 2 times of I, L value is 6 meter, so I am going to substitute that. Okay, so once you calculate how much is the stiffness value of joint B, similarly you can calculate for joint C also. Now CB is I by 3 and CD will be 2I by 6. So after solving this, you can solve your rotation factors also by taking the ratio of K by joint stiffness, multiplying it by minus 0.5. Okay, so this is how I calculated the rotation moment for BA, BC, BF, CD, CB and CD. Okay, so now let us solve the end moments from the Kinase method. So as we know, we have taken this part of the symmetry. So in this you can see that joint B is connected by BA, BAF and BC, and joint C is connected by CB and CD, right? So first let us write down all the fixed end moments. So as you know, you can see in the figure, the black ink from which I have written above the lines are representing the fixed end moment. So as we know, for columns we do not have any fixed end moment, only for beam we have fixed end moment. So for beam BF and CD we have calculated the fixed moment, which is minus 60 and 90. So I have written all those fixed end moments over here. Next, for your reference and for your understanding, whatever the values that I have written in blue ink will be representing M double dash values, which is the rotation moment at the near end. Okay, all the values which are written in the black ink are representing the values of rotation moment from the far end. Okay, right. So I think this is very much clear, and in the red ink whatever I have written is representing the rotation factor. Okay, so we have calculated the rotation factor. As you know, the same drill, either you can start from the top or you can start from the bottom. Okay, in previous problem what I did was I started from the top and I went in the downward direction and I calculated all the rotation moments. Now what I'll do is I'll start at joint B and I'll go to joint C. Okay, if I start at joint B, what I have to do, I have to take the summation of fixed end moment and summation of far end moments. So the far end moment for joint B will be M double dash CB and M double dash AB. So as we know, this is already equal to 0 because this is fixed end. So the other side will assume it to be 0, at M double dash CB to be 0. So minus 60 plus of 0 multiplied by the respective rotation factors. I'll write down the values here. Okay, so I have write down how much is M double dash BA, BF, BC. Okay, which is 10, 10, 10. Okay, now this completes the calculating the rotation moment for joint B. Now I'll go for joint C. So in joint C, what I'll do, I'll take the summation of fixed end moment, then I'll see what is the far end moment. So the far end moment at this side we'll consider it to be 0. Now on this side we have 10, so minus 90 plus of 10 multiplied by the respective rotation factors. I'll write down how much is M double dash CB, M double dash CD. Okay, which is 20 and 20. Okay, now this completes the first iteration. In the next iteration, I'll go to joint B. In joint B, the summation of fixed end moment is minus 60, but as we know the far end rotation is 20, so minus 60 plus of 20 multiplied by the respective rotation factors. I'll write down the values, so which is 6.668, 6.668 and 6.668. Okay, now again there is a revision of this far end rotation moment for joint C. So here also minus 90 plus of 6.668 multiplied by the respective rotation factor. I'll write down the values, which is 20.86. So I'll go for one more rotation. So in that I find that whatever the value that I calculate after this will be in precision only. The variation is only in terms of decimals, so I can freeze at the third step also. But if you want to go further, you can go for fourth iteration or fifth iteration to get more precise values till the third decimal point also. Okay, now anyway, so once I have freeze these values. You can see I have created a black box across the freezed values. So these are my freeze rotation moments. So next thing is to carry them over. So like for example, whatever the moment rotation moment I calculated for BA should be carried over to AB. Now whatever the moment that is carried over for BF is to be carried over to FB. Now see, in previous problem we had not done this. Okay, in previous problem we had not solved the moments at the section ends. Okay, if I had taken the section at this point, I had completely neglected this part, but here we are not going to do that. What we'll do is we'll consider these values. We'll transfer or we'll carry over whatever the rotation moment we calculated here to this side, which is 6.53. okay, now this is already 60, which is the fixed end moment. This is the carryover moment. Okay, once this is done, now we'll go to joint C. In joint C we have to carry over from BC to CB and CB to BC. Okay, now 6.53 is carried over here and 20.86 is carried over to this side. Now going to CD and DC, whatever the rotation moment you calculated at CD should be transferred to this side, which is 20.86. Now remember this, what is the difference that happened between the previous problem and this problem? Okay, so in previous problem I had cut the section at the center of the beam. Here I am not cutting at the center of the beam, I am taking out the entire beam itself. So that's why two changes that happened. One change is the stiffness values. Earlier the stiffness value is half of the stiffness, original stiffness. Here I'll complete the original stiffness itself, which is I by L. Okay, remember that. That is the first change happened. In the next change, what happens is in the Kinase diagram. In the Kinase diagram, you will not calculate the moments at the section where you had cut. Okay, but in this case I am calculating it. Okay, I hope you understand this. Okay, now once we solve this, what is that? I'll draw this table. In this table I am trying to solve how much is MAB, MBA, which are the end moments. So to calculate the end moments, first we need to write down all the fixed end moments, then we have to write 2 times of all the rotation moments at the near end, then we have to write the rotation moments at the far end. Okay, now going to MAB. Okay, at MAB, so here we know that the fixed end moment is 0 and near end rotation moment is also 0, so 0 0 are written, but the far end rotation moment is 6.53, which I have written here. So MAB will be equal to 6.53. Now going to MBA, similarly the fixed end moment at MBA is 0 and then the near end rotation moment is 6.53, so that's why I have to take the 2 times of 6.53, so 2 times of 6.53 is 13.06. Now substituting what is the far end rotation moments, the far end rotation moment, which is MAB, is 0, so that's why 0 has been substituted, and after solving the MBA will be 13.06. okay, now similarly we can go for M double dash BF, which is calculating the end moment at BF. So see here how much is the fixed end moment at BF, it is minus 60. Okay, now how much is the near end rotation moments, it is 6.53, so 2 times of 6.53 is 13.06. so the rotation moment at the far end is 0, right? So here also it will become 0, so taking the sum of this it will become minus 46.94. okay, now similarly we can calculate the other values too. So you can see here in case of calculating M DC and M FB, so what we done, we had written the fixed end moments, near end rotation moments are 0, the far end rotation moments for FB is 6.53, for DC it is 20.86. so I substituted here and solved, these are the values that I get. Okay, now you have calculated all the moments that are coming on one side of the symmetry. So we had solved for AB, BA, BF, CDs, and CB and BC. Okay, so we have solved all these moments. Now you can see that whatever the value that we solved using this diagram are written in blue ink, and whatever being replicated on the other side are written in the red ink. Okay, now you can differentiate between the values that are written here. The values over this side, if they are positive, if they go to that side it will become negative, and the values which are negative here, if they go to that side it will become positive. Okay, or vice versa, right? Now see here, if this is MAB, so Mij will be minus 6.53, here it is 6.53. Okay, this is what the change will happen. Now this is how we analyze the entire frame. Now in the beginning itself I told you why the moments in these columns is equals to 0. Okay, so the moments in these columns is equals to 0. We have calculated the moments for other elements. Now the next thing is to calculate the reactions for A, H and I. So after calculating the reaction, you can draw the shear force diagram and bending moment diagram. So draw the bending moment diagram and shear force diagram and show it to me. Okay, thank you.